If you have done any online shopping, you have undoubtedly seen recommendations pop up saying things like people who purchase this and that also purchase this and that. These suggestions are the result of a market basket analysis aimed at identifying frequent shopping habits. The goal is to increase sales by simplifying additional purchases for the customers. Besides cross-selling, this analysis can be exploited to offer pricing incentives on related products, to create product bundling, and to make assortment optimization. In physical store, such analysis provides suggestions on how to place products on the shelves to mutually promote their purchase. This kind of analysis is carried out using unsupervised learning algorithm called association rule mining. An association rule describes a relationship between variables or objects in a dataset. In addition to market basket analysis, association rule mining can be used for stock analysis, web log mining, social network analysis, medical diagnosis, bioinformatics, etc. One of the oldest and most frequently used algorithms for discovering association rules is called a priori. It is designed to operate on datasets containing transactions, such as point-of-sale transactions, which represent items bought together in a single basket by a customer. A priori uses a bottom-up approach, in which frequent subsets are extended one item at a time, a step known as candidate generation, and groups of candidates are tested against the data. The goal of this phase is to generate all the subsets of items with a number of occurrences larger than a minimum support threshold. To improve the efficiency of the generation of the frequent item sets, a priori exploits the anti-monotone property, which helps to reduce the search space. According to the anti-monotone property, all subsets of a frequent item set must be frequent, and if an item set is infrequent, all its supersets will be infrequent. A priori terminates when no more candidate sets can be generated. Once the frequent item sets are determined, the most prevailing association rules can be created and used to benefit the business. Each rule is composed of two different sets of items, called the antecedent and the consequent. The meaning is that when the items in the antecedent are in a transaction, then we expect to find these items also in the consequent. For instance, considering the supermarket domain, a rule could be: if butter and bread are the antecedent and milk is the consequent, the rule means that in a basket containing butter and bread, there is a high probability of finding milk too. When assessing the power and usefulness of association rules, some key metrics are considered. Support count, how often we can find items together in the same basket. Confidence, how often one or more items go into a basket when other items are already there. Lift, how more often two groups of items occur together than expected, if they were independent to each other. A powerful rule is expected to meet a minimum threshold of support and has high enough confidence or lift for practical purposes. Let's see now how it works with another example. In the table, we see a set of 9 transactions, and for each one, we have the items contained in each of them. We assume to be interested in rules with a minimum support count equal to 2 and a minimum confidence of 60%. The first step is to consider each item present in the dataset, candidate set, and to compare its support count with the minimum support count threshold. In this example, we can see that all the items are frequent enough. In the second step, starting from the frequent item sets identified during the previous step, we consider all the item sets with 2 items, and again, we test if they are frequent enough. In this case, only 6 of the original 10 item sets are frequent. Starting from these item sets, we generate the candidate set with 3 items. These new candidate sets are frequent only if all the subsets of them are frequent. So, for instance, the item set I1, I2, I3 may be frequent as the item sets I1, I2, I1, I3 and I2, I3 are frequent. On the other hand, the item set I2, I3, I4 is not frequent, as I3, I4 is not frequent. After the verification for each candidate set with 3 items, we can see which of them are frequent. Here, the generation of frequent item set stops, as there is no set with 4 items that is frequent. Now, given all the frequent item set with at least 2 items, we must generate all the strong rules, that is, all the rules whose confidence is above the minimum confidence threshold. For instance, looking at the item set I1, I2, I5, and checking in the transaction table, we see all the possible rules that can be generated with the related confidence values, which are obtained as the ratio between the support count of all the 3 items and the support count of the items in the antecedent of the rule. Only the rules with more than 60% of confidence are returned. To complete the procedure, we do the same check for item set I1, I2, I3. As we have just seen, the main limitation of the a priori algorithm is the time required to work with very large datasets, in which many frequent item sets can be generated. For instance, if there are 10,000 of frequent item sets with 1 item, it needs to generate more than 10 million candidates with 2 items. So, it will check for a lot of sets from the candidate item set, and it will scan the database several times for finding candidate item set, thus making the algorithm very slow. To overcome this issue, other approaches such as ECLAT and FBgrowth have been proposed. With this lesson, we have concluded our overview on unsupervised learning techniques. In the next lesson, we will start presenting the third subfield of machine learning, reinforcement learning.